Let's review the interpolation. Try to point out again a few important concepts. So here the idea is that you have x0, x1, xn, all right, and you have y0, y1 to yn, right? And we need to find a polynomial of degree n, right? Such that f xi is equal to yi, right? f xi equals to yi. And so basically you have a few points, right? You have a few points, and the goal is to find a polynomial to connect them, right? So here there's 3 points. You can find a quadratic polynomial, right? It interpolates them, meaning it passes through those points, right? We show it in one dimension, 1D function, but this can be done for multivariate function as well, all right? And I think a few important points. One is that if the points are distinct, then the polynomial, such polynomial, right? Such polynomial that we wanted, that the polynomial that pass through them exists and is unique, right? And in fact, we can construct it. It exists and is unique. We can construct it. Here's construction, all right? To construct it, an important tool that is very general is so-called characteristic polynomial, right? Which we write as Li of x, this function of x. Li of x. Okay, so first of all, it's degree n, and Li xj. So you give me I. I'm going to soon give you examples. But let's write down this and let's try to understand it, right? So you give me I. Well, Li of x is a polynomial degree n, such that if you evaluate at xj, you're going to get delta ij. Right? What is delta ij? Delta is the so-called canonical delta function. Is equal to 1 when I is equal to j. Is equal to 0 when I is not equal to j. This is a funny function, all right? It's a funny function. So in some sense, it characterizes the point xi, because if you evaluate at xi, you get 1. If you evaluate at anybody else, you get 0, right? You get 0. How do we do that? The Li of x is here is a notation for multiply things together, which again let me give you an example soon. So j is from 0 to n. J is not equal to I of x minus xj divided by xi minus xj. Right, xi minus xj. What does this mean? You know, if you look at a particular example, I hope it will be very clear, right? So if you do this, then you plug in xj, you're going to get 0. If you plug in xi, you're going to get 1 for fixed I. An example is that, let's say, you know, we have 3 points. Right, you have -1, 0, 1. All right, I have 3 points. 3 points. Right, there are like 3 values, maybe like that. Okay, maybe like that. So the I is 0, 1, 2, right? 0, 1, 2. I is the index. We get x0, x1, x2, all right? So he is x0, he is x1, he is x2. Is that okay? Right? If there are more points, you keep numbering them, right? It's 3 points. Okay? 0, 1, 2. So that's our I. I know many of you are not comfortable with this kind of notation, the dummy index, right? That's our I. Our I runs from 0 to 1 to 2, okay? So, which means we're going to get, we talk about Li of x, L0 of x, L1 of x, L2 of x, right? We're going to get 3 characteristic polynomials. It's a function. So it's of x. Now, we want, and you'll soon see why we want that, because it's so convenient for us to construct the resulting polynomial. We want it to be that the L0 of x, the function, corresponding to the first point, x0, right? We want it to be 0 at 1 and 2, x1, x2, I mean, okay? We want it to be 1 at its own point and 0 everywhere else. If you want to be 0 at any point, it should have a particular guy as its factor. So which means we're going to get, you want to be 0 at x1, 0 at x2. So you need x times x1 times x minus x1 times x minus x2. Because that way, if you evaluate x1, you're going to get 0. You're going to get 0 times something, right? If you evaluate at x2, you're going to get 0 as well. That's a trick. In our case, x1 is 0, so we're going to have x times x minus 1. Again, the reason is that if you plug in 0, you plug in 1, you are going to get 0. The only remaining condition, right, is that we need to make it 1 at what point? -1 at our own point, as the own point for this characteristic polynomial, right? So it must be 1 at -1. How to do that? You simply evaluate at x1 for whatever number you get, divided by that number, right? If you evaluate at -1, you're going to get -1 times -2, which is 2. So if you don't divide by anything, then you're going to get 2, which means if you divide by 2, you're going to get 1. No? Yes? So divide by 2. A generic formula is that you plug in the x0 into the numerator, right? You divide by that guy. So if I plug in x0 minus x1 times x0 minus x2, I'm going to get 2. Let's review, okay? For L1, you want to be 0 at x0 and x2. So you must have x minus x0 times x minus x2. And you want to be 1 at x1. So you evaluate your numerator at x1 and divide by that number. then for sure you're going to get whatever that number divided by that number. You're going to get 1, right? So it's x1 minus x0, x1 minus x2. This is a simple polynomial. As long as you know how to do it on paper, you can code that up. So in our case, x minus x0 is x minus 1, which is x plus 1, times x minus 1, which is x minus 1, right? It's x squared minus 1. Divided by, you evaluate at x1, which is 0. You evaluate at 0, you're going to get negative 1, right? So similarly, for L2, this is, you're going to get 0 to be at x0 and 0 at x1. So you need the factor x minus x0 and x minus x1. And normalize it, again, this is normalization. You normalize it so it's equal to 1 at your point. Right? So it's x2 minus x0 times x2 minus x1. Right? Which is, you plug in, x0 is 0, x0 is negative 1, so it's x plus 1 times, so it's x plus 1 times x divided by, plug in your 2, which is 2 plus 1 times 2, you get 6, right? Oh, no, you plug in x2, which is 1, and plug in 1, you're going to get 2, right? Get 2. Is everybody following this? This is, let's make sure. Once we have those things, right? Once we have those things, then that f of x, right? That's that f of x that we wanted above, right? This is denoted. It's denoted. We're going to denote it by in of x, right? From now on, in of x, because it's interpolating at degree n, so it's in. But again, that's just notation. We're going to use it here. We don't have to, right? There's something we agree with here. Once you have those magic polynomials, the basic polynomials, what you do is that I'm going to take each of them, all right, Li of x. I'm going to multiply that by yi. I'm going to add up from 0 to n. Now, that's your answer. That's why it's called construction. We can construct a polynomial for that purpose. All right. So what's going on here is that in, right? That is in the red box. That in x, right? If you check in, if I plug in x any I, all right? X, let's use j, any j, because we have the I for the summation. Let's check, because we want that to be in of xj. We want that to be what? What's it? Yeah, we want the whole function is f, right? We want the value at xj to be yj, right? To be yj. We want that guy. F at xi is yi, which means f of at xj is yj. So in xj is yj. If we check that, then we're done. Right? So what is this thing? It's a summation. It's a sum I from 0 to n of my yi, li. Yi is constant, some constant. Li is that function we just made up. Li of x, you evaluate at xj. At xj, right? Now the magic happens because you have you have a fixed j, right? You evaluate xj, fixed j, and your I is changing from 0 to n. For any I that's not equal to j, your Li xj is equal to 0, right? 0. So, I mean, if I write one more step here, right, you're going to get y0, L0 of xj plus y1, L1 xj plus somewhere yj minus 1, Lj minus 1 at xj, right, plus yj, Lj at xj. These are all these functions, but all evaluate at the same point, plus yj plus 1, Lj plus 1 at xj, plus all the way to the end, right? Yn, Ln, xj. If you didn't see right away it's equal to yj, then you need to expand this, like what I'm doing here, right? But from now on, I'm going to assume you can see it. So the only term that survive is this guy. That's 1. And that's 0, that's 0, all the way, that's 0, that's 0, 0, right? All these guys. Okay, because this function evaluate at the corresponding number, xj is 1, otherwise it's 0. So even though the m plus 1 terms, that's key, right? There are m plus 1 terms, but only one term is non-zero. Everybody else is 0. That's what's going on. So this is equal to yj times 1, which is equal to yj. Check. All right? And that's true for any j. All right? Questions? This way is called Lagrange form, right? Lagrange form. And a note 1 is that look at the definition of Li, right? Li is that guy, is x minus everybody else divided by Li x I evaluate at those, right? On the evaluate the numerator at xi. Another way of writing this down, and sometimes is more convenient, is using a notation. If we define omega m plus 1, right? It's Greek letter omega. It looks like W, but it's a little bit curvy than W, right? Omega m plus 1, omega sub m plus 1 x. So above we multiply x minus something, right? And we skipped I, right? And then when you change your I, it's kind of that's not symmetric, right? You for x0 you're skipping x minus x0. For x1 you're skipping x minus x1, right? So if we put everybody together and call that guy omega m plus 1, so he is simply x minus xj, and multiply all of them together. J is from 0 to n. We're not skipping anything. Above we're skipping xi, right? To make it work, what we just talked about work. Okay. Then, so we define that. We're going to use that fairly often, a few times. But in particular, you can prove which is a very simple exercise. We can prove that this INX we did above, all right, is actually the summation I is from 0 to n. We had yi. We had that red box, right? This guy. This is our result. Yi times Li. So if we want to write it in terms of omega n plus 1, okay, omega n plus 1, it's actually yi times omega n plus 1 of x divided by x minus xi. We included everybody now, right? So we need to divide by x minus xi term to recover what we had. It's Li. The Li has no x minus xi. So if you divide by x minus xi, you're going to recover that, right? You're going to recover that. And as a constant, turns out to be omega n prime xi. I mean n plus 1 prime xi. That function evaluate. You take the derivative and evaluate at xi, you're going to get what we had above, the new denominator. That's one simple application of product rule. All right, then you're going to see. If you need to evaluate the derivative as that newly defined function. So this is omega n plus 1 for those. This is n plus the same function as above. You take a derivative and then evaluate at xi. Right? So what are we having? We're having is this guy, right? Is this and this, right? The two parts. So the red part should be the numerator of our Li. The purple part is the denominator of our Li that we're done. Okay? And again, just take the derivative, use the product rule, and then evaluate, you'll see. All right? That'll be one of the next homework problems. So what I plan to do next is we talk about the construction of what I want to review or talk in a bit more detail is the interpolation error, right? Interpolation error. So for many settings, for some setting, you're given discrete data, like what we just plotted above. You have 3 points. You draw a polynomial that pass through them, right? Okay. And for other settings, you're actually given a function. Remember, we talked about, some functions are very hard to evaluate on computers, but polynomials are easy to evaluate. So when you have a function, right? You get a magic function, or whatever complicated function, and you want to deal with it on computer. Sometimes you need to convert that into polynomial. I mean, one way, as we have done, is Taylor expansion, right? It's an approximating polynomial. Okay, you should think of that as related to here. That is, remember when we review Taylor expansion, we replace f by a polynomial, but we match the value and the derivative and second derivative and so on and so forth. We keep increasing that, right? We keep matching more and more at that point, alpha. Remember, right? We match the derivative, we match the second derivative and so on and so forth. Okay? So here is a second kind of approximation when you are given a function f, right? Again, here we are given a general function, f of x, right? the so-called the so-called interpolant. All right, interpolant, which we're going to denote it by I sub n of f of x. All right, is the degree n polynomial such that if you evaluate f at the xi, you're going to match the function value. You match the function value is equal to f of xi. Okay. Let's say you have some sort of function, right? Some sort of function, and then we have a few points. Right? This blue guy is a function f of x. It's not necessarily polynomial. Any function you have to deal with, right? And its interpolant is that x0, x1, x2, x3, x4, right? Its interpolant is a polynomial that this is a interpolant. This is a polynomial, right? A polynomial. This one is not necessarily a polynomial. So this is you approximate a general function by a polynomial. Okay. So again, as I just said, maybe I should write it down. Basically, two ways to approximate a general function f, right? One is Taylor expansion. Two is this polynomial interpolation. That's where the keyword interpolation comes in. You're going to find the polynomial. Again, they're both polynomials, but they're very different. Here is, we just make sure it recovers the function value at a whole bunch of points. Right? Over there is it matches the derivatives. Right? So, what do they match? So what does it match? Here it matches f, the i's derivative, at the fixed point alpha, at a given point alpha, the neighborhood they want to do Taylor expansion, right? Matches at a single point, matches a multiple derivative at a single point. Over here, it matches the function value at xi, and the i's from 0, 1, 2, and so forth. So here also I0, 1, 2, so on so forth. When I0 is zero's derivative, is function itself. If you really understand this, that's pretty good, right? You understand, you know, Taylor series in a decent level. So that's basically the idea of polynomial interpolation. And as you see, as you saw also on last Thursday from the experiment, all right? So we want to approximate by a polynomial, and from this picture as well, you see the gaps and the gaps. And then we can recover exactly. If this guy is not a polynomial, there's no way this error is 0 everywhere. There's no way, right? You're going to get some error. And that's what the interpolation error means. The title of this, what I just wrote down, right? So the error, we need to figure out when we use polynomial to approximate a function that's not a polynomial. The first question is, what kind of error are you making, right? What kind of error are you making? So the error ENX, this is the difference f of x minus IN f of x, right? IN f of x. And f of x. And there's a theorem which I'm going to prove it, and I think, you know, because it's a proof, the proof is it's fun, and also we can review some of the calculus, but I'm not going to ask you to prove in the exam. That's basically not required, right? But let's try to review this together, and in the meantime, we're going to review some of the important result that we used already a few times, and we need to use again in the future, right? And again, we need them to be extinct if x0, x1. I mean, let's make them extinct. Not extinct, distinct. Are distinct, so they're all different points, right? Then this arrow, then we know that exists polynomial, right? The polynomial exists and is unique. Okay. So this arrow, the approximation arrow, all right, is actually equal to f to the m plus 1 derivative at some c divided by m plus 1 factorial times omega m plus 1 that omega we defined above for some c in some domain that contains in let's use omega x, and the omega x is an interval, right? An interval that contains x, x0, x1, xn, right? Xn. So you're given n plus 1 points. You do your interpolation. All right, you do your interpolation. We need n plus 1 points to do a degree n interpolation, right? Like 3 points, you get a polynomial degree 2. Okay? That's ax squared plus bx plus c, right? And so those n plus 1 points, and then you're asking yourself, we're asking ourselves that what is the error? What is the error at some x, right? At some x. Here is your x. At that x. So the x might be different from x0, x1, all the way to x2. That's why I'm saying, this the c, again, we don't know what c is, but c is among those points. Okay? Between any of those 2 points. All right? We're going to prove that soon. But let's write down what I just said, just very briefly. So we're going to prove that. What I said is that what I just emphasized, right? I don't know if everybody was paying attention. When we want a degree n, we actually need n plus 1 points, right? So degree n takes n plus 1 points. Again, we did a quadratic polynomial, right? So, I mean, which reminded me of a very basic way to find the interpolants, to find what we did on above the construction, right? You can use, if you have 3 points. Let's see, we have 3 points, right? That produces a quadratic polynomial, right? Quadratic polynomial. So 3 points for quadratic polynomial degree 2, n is 2, right? And we know of course, y is ax squared plus bx plus c. That I hope everybody is comfortable. And in fact, the interpolation should probably be started with that. But this is a review. So this is I2, right? I2x, degree 2, I2x. You see, for I2x, you have 3 unknowns, A, B, C, right? I, B, C. And you could just set up that you want I2x0 is y0, I2x1 is y1, I2x2 is y2. Okay. Which then gives you a what? A linear system for ABC. Right, linear system for ABC. Okay? Was that talked about last Thursday? So what are we having? We're having this A, B, C, right? I2 evaluate at this is just a way to order them. Let me order them like C, B, A, right? C, B, A. To write down this equation, you're going to get 1, so 1 times C, right? B times x0, right? x0, so it's x0. Here is x0 squared. This is equal to y0, right? So you put y0 there. That's the first equation. I'm doing this will give you a first equation. Can everybody do that? And we continue, they're going to get 1 x1, x1 squared, 1 x2, x2 squared. Here's y1, here's y2. Yeah. And that's of course more general than just 3 points. What I'm showing you here is degree n takes n plus 1 points, right? So in general, this matrix, when for x0, x1 to xn, if you have n plus 1 points, all right, you're talking about degree n polynomial. So that the original INX, again, this is not proving the theorem yet. This is A a0 plus a1x plus a2x squared all the way to an xn. When n is 2, we can use ABC. When n is 17, you cannot keep using those. So let's use the same letter but add a subscription, right? A1, A2, and so on and so forth. In that case, we also have a little linear algebra system, which is 1 x0 squared all the way to x0 to the what? To the what power? N, yes, N, right? This should be multiplied with A0, A1, all the way, A2, all the way to AN. AN would hit X0 to the N. This must be equal to the Y0. And we continue writing. So this is 1, x1 squared, x1 to the N. 1, xn squared, all the way xn to the N. All right, xn to the N. Xn to the N. Right, let's review. So yes, that's a so-called Van Neumann matrix. Van Neumann matrix. A second approach, as we just said, a second approach to prove the existence, the uniqueness of the interpolation of that polynomial is that you look at this system and you convince yourself, again, that's a classical result. This linear system has a unique solution, which is the matrix is non-singular, right? And one way to show matrix is non-singular is to calculate its so-called determinant. Determinant must be what? Must satisfy what condition for it to be non-singular? Non-zero, exactly. Its determinant is not 0, all right, which shows is non-singular, which also shows there is a unique solution to this linear system. So you solve it, you get a coefficients. That's your polynomial, right? Other than, they'll be like different from the way we just did. We constructed a polynomial. They're both fine, okay? So the trick is that we define an auxiliary function, right? G of t, this is equal to ENT for a given x, x0 all the way to xn, and then you have to talk about the arrow at some x. X is also given now, all right? And we define a function of t. This is minus omega n plus 1 t enx divided by omega n plus 1 x. Right? So again, the x, x0, x1, xn, they're all given. We could talk about how to motivate this. How do we know we define it that way? But I don't want to make that the point here. The point here is inside is the proof. What is the calculus we're reviewing? That's useful for us. All right. Anyway, let's assume magically we know we can define this function to help us. A few of the things that we're going to rely on again has been useful and will continue to be useful for our purpose. If we look at this function, right? If we if t is equal to xi, right, for t to be one of those xi's, I is 0, so here I is 0, 1, all the way to n, all right, for all those n plus 1 points. If I evaluate at the xi, okay, so you plug in xi for t, right? That's what we mean by evaluation. Evaluate at xi, all right, en xi, minus omega n plus 1 t at xi, right, times that en x again is fixed number, which we don't really care. Now, what is en xi? What is omega n plus 1 xi? That's something, if you look at the picture, and its definition of n plus 1, all right? What is the definition? It's right here, yes. So this is 0 en of xi 0 because, you know, it recovers the function value at xi, so the arrow is 0. And omega n plus 1 of xi 0 because omega n plus 1 contains all the factors x minus those points, right? Contains x minus xi, so it's 0. Times something about x we don't really know, but that's fine because it's multiplied by 0, so you're going to get 0, right? You're going to get 0. Now, the tricky part, the nice thing of defining t that way is that you evaluate t at xi. At xi. We assume x is not one of those xi's because if x is one of those xi's, the theorem is trivial. The error is 0 at x. We have nothing to prove if x is one of those xi's. Right, so assume they are not the same. In this case, if we plug in x, you're going to get en x, right? Plug in x for t, minus omega n plus 1 x times en x divided by omega n plus 1 x. You're going to get 0 because it's en minus en, right? En minus en. We are canceling this, right? It's en minus en, so we get 0. Right? You get 0. It's very quite a revealing and interesting proof. So the function, our function, which means so, which our function g of t has. We found many zeros, right? So there may be some other zeros that we don't know. But how many we have found? How many have we found? Let's count. So we have m plus 2 zeros. Right? They're zeros. Again, we assume x is not equal to xi. Otherwise, the result of the theorem is trivial because the error at xi is 0. If x is one of the xi, the error at x is 0. You have nothing to prove. Right? And now, the picture that I've talked about many times, if you have that picture, right, that picture, if you connect the 2 points, and you shift it, and there should be a point in the middle that has a slope, that has a tangent. The derivative is equal to that slope, right? Equal to that slope. Now, we sort of rotate this, right? Rotate this picture to, now we'll talk about zeros. So if we have some function, it's equal to 0 at those 2 points. Right? They're both 0. That picture, that theorem still applies, right? Which means if we shift this to maybe here, that's our new Cassie there, right? From that old picture. The derivative at Cassie is equal to what? Yeah, 0, exactly. It's a slope, right? The slope in this special case is 0. So which means if we take the derivative, right? If x is x somewhere, right? X somewhere between, among x0 to xn, n plus 2 points. Those n plus 2 zeros, we can order them. We don't really know now, but that doesn't matter. That particular order. Between any two of those n plus 2, you can find a 0. You can find a point whose derivative is 0. Right? The g prime, again, g prime is a function. That's the derivative of g. Has a 0 between any pair of points of the set, right? X, x0, x1, xn. You take any pair because of that theorem that we know we can find a 0 in between. So in particular, if you order them from smallest to largest, you just go, right? Let's assume our x is smallest. Here is x. Maybe x is between x0 and x1, x1, x2, all the way here is xn minus 1, here is xn. So I'm going to get, by our analysis, we're going to get a 0 between any two of them, right? We're going to get a 0 for the derivative. How many are we having? n plus 1, exactly, right? Well, we have 1 between any of the two, okay? So you have 3 points, A, B, C. Then between A, B, between B, C, you're going to get 2. So g prime of t has at least we can identify, now it's n plus 1 zeros, right? Zeros. Does that make sense? Going, the g prime has that many zeros, which means the g double prime t has at least how many zeros? N, because g double prime is a prime of g prime, right? Okay, so this means in the very end, if you take g n plus 1's derivative at t, and how many zeros does this have? It's a pattern, right? 1 derivative at n plus 1, 2 derivative at n, 3 derivative at n minus 1. What's the pattern? Each time you raise that by 1, you have 1 less. You only have 2 points, you only get 1 point in the middle that has 0 derivative, right? So if the number of derivatives goes up, his goes down, just need to figure out, like, is it 1 or 2 or 0? We did this in a couple of times already, right? If this increased by 1, this decreased by 1, that means the sum is not changing. Look at the sum. That's it. Look at the sum. M1 plus n plus 1 is n plus 2. 2 plus n is n plus 2. The sum is not changing, which means n plus 1 is 1. Exactly, 1. 1. Okay? That's a trick. Look at the sum. One. Now, we assume that 1 point is c, or just denoted by c, which means our g, the function that we don't know, but we do know it has 1, 0. All right, 1, 0. And we know then the next is interesting again, a little bit more calculus, right? So let's, that's our definition of gt above, right, over there. Let's write that down. So the g of t is simply ent minus omega n plus 1 t times enx divided by omega n plus 1 x. We can differentiate that. N plus 1 is derivative, and interesting things will happen, right? If we evaluate this to the n plus 1's derivative at t. Okay, at t. This is, of course, en, that's a function of t as well, to the n plus 1's derivative at t, right? Minus this omega n plus 1 to the n plus 1's derivative at t, right? This function of t, we'll talk about the, we take the n plus 1's derivative with respect to t. The x is constant, so we don't do anything. Just keep writing enx divided by omega n plus 1x. Okay? All right? So what is this? We know en is f minus en is f minus inf, right? En is error. The degree n, here inf is a degree n polynomial, is interpolant. The degree n, if you take n plus 1 the derivative, what do you get? Degree 2, degree 1, you take second derivative. 0. 0. Okay? 0. So that's good. Like, that's the things that I was talking about, the basic things here, right? The degree n, if you take n plus 1 derivative, you are going to get 0. So this en, because it's f minus degree n, so this is f. So f can be any function, of course. So it's f. We don't know what is n plus 1's derivative. Just write it down. But we do know the second part is 0. So this is our first term. Okay. Our second term, our this term, I'm claiming that's m plus 1 factorial, which I'm going to explain soon, very quickly. This is enx over omega n plus 1x. Right? Now, we know this guy at c equal to 0. So if we just did above, right? If at c, we know it's 0. But we now concluded is f n plus 1 derivative at c, now t is c, right? Minus n plus 1 factorial enx over omega n plus 1 x. That's exactly what we need to prove. Right? That's exactly what we need to prove. Solve for enx, then we're done. The only thing that remains is how to conclude that n plus 1 derivative is equal to n plus 1 factorial, right? I'm going to give you a clue here, right? I'm going to give you a clue here and leave that exercise. Once you see my clue, it should be very easy. So why that omega n plus 1 to the n plus 1's derivative at x is equal to n plus 1 factorial. The reason is that omega n plus 1 x is x minus x0 times x minus x1 times everybody together, right? This is the degree n plus 1. The first term is x to the n plus 1, right? Because you take x from each parenthesis. You're going to get x to n plus 1. And plus whatever remains is a degree n polynomial, right? That's my hint. Sorry for running over time.